हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज मैं करने वाली हूँ क्लास 11th यूनिट 8 रिडॉक्स रिएक्शंस। सो बहुत कम चैप्टर बचे हैं आपके क्लास 11 के लिए और बहुत जल्दी आपके पास में इसके पार्ट 2 की भी केमिस्ट्री की कंप्लीट ऑडियो बुक आ जाएगी और फिर उसके बाद में 12th की भी आ जाएगी। और ये सब कुछ आपके नीट एग्जाम के पहले पहले ही हो जाएगा, उम्मीद है काफ़ी पहले हो जाएगा, ताकि आप अच्छे से रिवाइज कर सकें। बस आपको क्या करना है, आपको अपने दोस्तों के साथ भी शेयर करना है ताकि उनको भी इसकी हेल्प मिल सके और आपको उनकी ब्लेसिंग्स मिल सके। सो चलिए टाइम वेस्ट नहीं करते हैं। और हाँ, एक और बात, अगर आप लोगों को लगता है कि आपकी हेल्प कर रही है तो इसे लाइक कीजिएगा और अगर चैनल पे नए हैं तो सब्सक्राइब कर लीजिए, काम आती रहेगी। चलिए स्टार्ट करते हैं। यूनिट 8 रिडॉक्स रिएक्शंस। Where there is oxidation, there is always reduction. Chemistry is essentially a study of redox systems. Chemistry deals with varieties of matter and change of one kind of matter into the other. Transformation of matter from one kind into another occurs through the various types of reaction. One important category of such reaction is redox reactions. A number of phenomena, both physical as well as biological, are concerned with redox reactions. These reactions find extensive use in pharmaceutical, biological, industrial, metallurgical, and agricultural areas. The importance of these reactions is apparent from the fact that burning of different types of fuels for obtaining energy for domestic, transport, and other commercial purposes, electrochemical processes for extraction of highly reactive metals and nonmetals, manufacturing of chemical compounds like caustic soda, operation of dry and wet batteries, and corrosion of metals fall within the purview of redox processes. Of late, environmental issues like hydrogen economy, use of liquid hydrogen as fuel, and development of ozone hole have started figuring under the redox phenomena. 8.1 Classical idea of redox reactions, oxidation and reduction reactions. Originally, the term oxidation was used to describe the addition of oxygen to an element or a compound. Because of the presence of dioxygen in the atmosphere, that is 20% approximately, many elements combine with it, and this is the principal reason with why they commonly occur on the earth in the form of their oxides. The following reactions represents oxidation processes according to the limited definition of oxidation. 2Mg plus O2 gives out 2MgO, S plus O2 gives out SO2. In reactions 8.1 and 8.2, the elements magnesium and sulfur are oxidized on account of addition of oxygen to them. Similarly, methane is oxidized owing to the addition of oxygen to it. CH4 plus 2O2 gives out CO2 plus 2H2O. A careful examination of reaction in which hydrogen has been replaced by oxygen prompted chemists to reinterpret oxidation in terms of removal of hydrogen from it, and therefore the scope of term oxidation was broadened to include the removal of hydrogen from a substance. The following illustration is another reaction which removal of hydrogen can also be cited as an oxidation reaction. 2H2S plus O2 gives out 2S plus 2H2O. As knowledge of chemists grew, it was natural to extend the term oxidation for reactions similar to, which do not involve oxygen but other electronegative elements. The oxidation of magnesium with fluorine, chlorine, and sulfur, etc., occurs according to the following reactions. Mg plus F2 gives out MgF2, Mg plus Cl2 gives out MgCl2, Mg plus S gives out MgS. Incorporating the reactions within the fold of oxidation reactions encouraged chemists to consider not only the removal of hydrogen as oxidation, but also the removal of electropositive elements as oxidation. Thus, the reaction 2K4 FeCN whole 6 plus H2O2 gives out 2K3 FeCN whole 6 plus 2KOH is interpreted as oxidation due to the removal of electropositive element potassium from potassium ferrocyanide before it changes to potassium ferricyanide. To summarize, the term oxidation is defined as the addition of oxygen, electronegative element to a substance, or removal of hydrogen, electropositive element from a substance. In the beginning, reduction was considered as a removal of oxygen from a compound. However, the term reduction has been broadened these days to include removal of oxygen, that is electronegative element, from a substance, or addition of hydrogen, that is electropositive element, to a substance. According to the definition given above, the following are the examples of reduction processes. 2HgO on heat, it gives out 2Hg plus O2. Removal of oxygen from mercuric oxide. 2FeCl3 plus H2 gives out 2FeCl2 plus 2HCl. Removal of electronegative element chlorine from ferric chloride. CH2 double bond CH2 plus H2 gives out CH3 single bond CH3. Addition of hydrogen is here. And 2HgCl2 plus SnCl2 gives out Hg2Cl2 plus SnCl4. Here the addition of mercury to mercuric chloride. In reaction 8.11, simultaneous oxidation of stannous chloride to stannic chloride is also occurring because of the addition of electronegative element chlorine to it. It was soon realized that oxidation and reduction always occur simultaneously, as will be apparent by re-examining all the equations given above. Hence, the word redox was coined for this class of chemical reactions. 8.2 Redox reactions in terms of electron transfer reactions. We have already learned that the reactions 2Na plus Cl2 gives out 2NaCl, 4Na plus O2 gives out 2Na2O, 2Na plus sulfur gives out Na2S are redox reaction because in each of these reactions sodium is oxidized due to the addition of either oxygen or more electronegative element to sodium. Simultaneously, chlorine, oxygen and sulfur are reduced because to each of these, the electropositive element sodium has been added. From our knowledge of chemical bonding, we also know that sodium chloride, sodium oxide, and sodium sulfide are ionic compounds and perhaps better written as Na plus Cl negative, Na positive whole twice to O2 negative, and Na positive whole twice S2 negative. Development of charges on the species is produced suggests us to rewrite the reaction in the following manner. Here you can see the reactions and how can we write it. The gain of electron and the loss of electron. For convenience, each of the above processes can be considered as two separate steps, one involving the loss of electrons and the other the gain of electrons. As an illustration, we may further elaborate one of these, say the formation of sodium chloride. 2Na plus 2Na positive gives out 2 electron, Cl2 plus 2 electron gives out 2 Cl negative. Each of the above step is called a half reaction, which explicitly show involvement of electrons. Sum of the half reactions gives the overall reaction. 2Na plus Cl2 gives out 2Na positive, Cl negative or 2NaCl. Reactions 8.12 to 8.14 suggest that half reactions that involve loss of electrons are called oxidation reactions, and similarly the half reaction that involve gain of electrons are called reduction reactions. It may not be out of the context to mention here that the new way of defining oxidation and reduction has been achieved only by establishing a correlation between the behavior of species as per the classical idea and their interplay in electron transfer change. In reactions 8.12 to 8.14, sodium which is oxidized acts as a reducing agent because it donates electron to each of the elements interacting with it and thus helps in reducing them. Chlorine, oxygen and sulfur are reduced and act as oxidizing agent because these accept electrons from sodium. To summarize, we may mention that oxidation, loss of electron by any species, reduction, gain of electron by any species, oxidizing agent, acceptor of electron, reducing agent, donor of electrons. 8.2.1 Competitive electron transfer reactions. Place strip of metallic zinc in an aqueous solution of copper nitrate as shown in figure 8.1 for about 1 hour. You may notice that the strip becomes coated with reddish metallic copper and the blue color of the solution disappears. Formation of zinc 2 positive ions among the products can easily be judged when the blue color of the solution due to CO2 positive has disappeared. If hydrogen sulfide gas is passed through the colorless solution containing Zn2 positive ions, appearance of white zinc sulfide ZnS can be seen on making the solution alkaline with ammonia. The reaction between metallic zinc and the aqueous solution of copper nitrate is Zn plus Cu2 positive gives out Zn2 positive plus Cu. In reaction, zinc has lost electrons to form Zn2 positive and therefore zinc is oxidized. Evidently, now if zinc is oxidized, releasing electrons, something must be reduced accepting the electrons lost by zinc. Copper ion is reduced by gaining electrons from the zinc and reaction 8.15 may be written as, here you can see the reaction and here is the diagram 8.1 redox reaction between zinc and aqueous solution of copper nitrate occurring in a beaker. At this stage, we may investigate the state of equilibrium for the reaction represented by equation 8.15. For this purpose, let us place a strip of metallic copper in a zinc sulfate solution. No visible reaction is noticed and attempt to detect the presence of Cu2 positive ions by passing H2S gas through the solution to produce the black color of cupric sulfide. CuS does not succeed. Cupric sulfide has such a low solubility that this is an extremely sensitive test, yet the amount of Cu2 positive formed cannot be detected. We thus conclude that the state of equilibrium for the reaction greatly favors the product over the reactants. Let us extend electron transfer reaction now to copper metal and silver nitrate solution in water and arrange a setup as shown in figure 8.2. The solution develops blue color due to the formation of Cu2 positive ions on account of the reaction. Here you can see the reaction Cu plus 2Ag positive and the release of electron and the gain of electron, and the final product is Cu2 positive plus 2Ag. Here Cu is oxidized to Cu2 positive and Ag positive is reduced to Ag. Equilibrium greatly favors the product Cu2 positive and Ag. By way of contrast, let us also compare the reaction of metallic cobalt placed in nickel sulfate solution. The reaction that occurs here, Co plus Ni2 positive gives out CO2 positive plus Ni. Here you can see the reaction also. And here is the figure 8.2 redox reaction between copper and aqueous solution of silver nitrate occurring in a beaker. At equilibrium, chemical tests reveal that both Ni2 positive and CO2 positive are present at moderate concentrations. In this case, neither the reactants nor the products are greatly favored. This competition for release of electrons incidentally reminds us the competition for release of protons among acids. The similarity suggests that we might develop a table in which metals and their ions are listed on the basis of their tendency to release electrons, just as we do in the case of acids to indicate the strength of the acids. As a matter of fact, we have already made certain comparisons. By comparison, we have come to know that zinc releases electrons to copper and copper releases electrons to silver, and therefore the electron releasing tendency of the metal is in the order of Zn is greater than Cu is greater than Ag. We would love to make our list more vast and design a metal activity series or electrochemical series. The competition for electrons between various metals helps us to design a class of cells named as galvanic cells, in which the chemical reactions become the source of electrical energy. We would study more about these cells in class 12. 8.3 Oxidation Number. A less obvious example of electron transfer is realized when hydrogen combines with oxygen to form water by the reaction. 2H2 plus O2 gives out 2H2O. Though not simple in its approach, yet we can visualize the hydrogen atom as going from a neutral zero state in H2 to a positive state in H2O. The oxygen atom goes from a zero state in O2 to a negative state in H2O. It is assumed that there is an electron transfer from hydrogen to oxygen, and consequently H2 is oxidized and O2 is reduced. However, as well as we shall see later, the charge transfer is only partial and is perhaps better described as an electron shift rather than a complete loss of electron by hydrogen and gain by oxygen. What has been said here with respect to equation 8.18 may be true for a good number of the other reactions involving covalent compounds. Two such examples of this class of the reactions are H2 plus Cl2 gives out 2HCl, CH4 plus 4Cl2 gives out CCl4 plus 4HCl. In order to keep track of electron shifts in chemical reactions involving formation of covalent compounds, a more practical method of using oxidation number has been developed. In this method, it is always assumed that there is a complete transfer of electron from a less electronegative atom to a more electronegative atom. For example, we rewrite the equation 8.18 to 8.20 to show charge on each of the atoms forming part of the reaction. Here you can see all the three reactions and their oxidation states or the transfer of electrons. It may be emphasized that the assumption of electron transfer is made for bookkeeping purpose only, and it will become obvious at a later stage in this unit that it leads to the simple description of redox reaction. Oxidation number denotes the oxidation state of an element in a compound ascertained according to a set of rules formulated on the basis of that electron pair in a covalent bond belongs entirely to more electronegative element. It is not always possible to remember or make out easily in a compound or ion which element is more electronegative than the other. Therefore, a set of rules has been formulated to determine the oxidation number of an element in a compound or ion. If two or more than two atoms of an element are present in the molecule or ion, such as Na2S2O3 or Cr2O7, 2 negative, the oxidation number of the atom of that element will then be the average of the oxidation number of all the atoms of that element. We may at this stage state the rules for the calculation of oxidation number. These rules are: number 1, in elements in the free or the uncombined state, each atom bears an oxidation number of 0. Evidently, each atom in H2, O2, Cl2, O3, P4, S8, Na, Mg, Al has the oxidation number 0. Number 2. For ions composed of only one atom, the oxidation number is equal to the charge on the ion. Thus, sodium ion has an oxidation number of +1, Mg2 positive +2, Fe3 positive +3, Cl negative -1, O2 negative -2, and so on. In their compounds, all alkali metals have oxidation number of +1 and all alkaline earth metals have an oxidation number of +2. Aluminum is regarded to have an oxidation number of +3 in all its compounds. Third, the oxidation number of oxygen in most compound is -2. However, we come across two kinds of exceptions here. One arises in the case of peroxides and superoxides, the compounds of oxygen in which oxygen atoms are directly linked to each other. While in peroxides, H2O2, Na2O2, each oxygen atom is assigned an oxidation number of -1. In superoxide, example KO2, RbO2, each oxygen atom is assigned an oxidation number of -1/2. The second exception appears rarely, that is when oxygen is bonded to fluorine. In such compounds, example oxygen difluoride and dioxygen difluoride O2F2, the oxygen is assigned an oxidation number of +2 and +1 respectively. The number assigned to oxygen will depend upon the bonding state of oxygen, but this number would now be a positive figure only. Number 4, the oxidation number of hydrogen is +1. Except when it is bonded to metals in binary compounds, that is, compounds containing two elements. For example, in LiH, NaH and CH2, its oxidation number is -1. Fifth, in all its compound, fluorine has an oxidation number of -1. Other halogens, chlorine, bromine and iodine also have an oxidation number of -1. When they occur as halide ions in their compounds, chlorine, bromine and iodine, when combined with oxygen, for example in oxoacids and oxoanions, have positive oxidation numbers. Number 6. The algebraic sum of the oxidation number of all the atoms in a compound must be 0. In polyatomic ion, the algebraic sum of all the oxidation number of atoms of the ion must equal to the charge on the ion. Thus, the sum of oxidation number of the 3 oxygen atoms and 1 carbon atom in the carbonate ion CO3 2 negative must equal -2. By the application of above rules, we can find out the oxidation number of the desired element in a molecule or in an ion. It is clear that the metallic elements have positive oxidation number and non-metallic elements have positive or negative oxidation number. The atoms of transition elements usually display several positive oxidation states. The higher oxidation number of a representative element is the group number for the first two groups and the group number -10. For the other groups. Thus, it implies that the highest value of oxidation number exhibited by an atom of an element generally increases across the period in the periodic table. In the third period, the highest value of oxidation number changes from 1 to 7 as indicated below in the compounds of the elements. A term that is often used interchangeably with the oxidation number is the oxidation state. Thus, in CO2, the oxidation state of carbon is +4. That is also its oxidation number, and similarly, the oxidation states as well as oxidation number of oxygen is -2. This implies that the oxidation number denotes the oxidation state of an element in a compound. Here you can see the table. The oxidation number or state of a metal in a compound is sometimes presented according to the notation given by German chemist Alfred Stock. It is popularly known as a Stock notation. According to this, the oxidation number is expressed by putting a Roman numeral representing the oxidation number in parentheses after the symbol of the metal in the molecular formula. Thus, Aurous chloride and auric chloride are written as Au1Cl and Au3Cl3. Similarly, stannous chloride and stannic chloride are written as Sn2Cl2 and Sn4Cl4. This change in oxidation number implies change in oxidation state, which in turn help to identify whether the species is present in oxidized form or reduced form. Thus, Hg2,1Cl2 is the reduced form of Hg2Cl2. The idea of oxidation number has been invariably applied to define oxidation, reduction, oxidizing agent, that is oxidant, reducing agent, that is reductant, and the redox reaction. To summarize, we may say that number 1, oxidation, an increase in the oxidation number of the element in the given substance. Reduction, a decrease in the oxidation number of the element in the given substance. Third, oxidizing agent, a reagent which can increase the oxidation number of an element in a given substance. These reagents are called as oxidants also. Reducing agents, a reagent which lowers the oxidation number of an element in a given substance. These reagents are also called as reductants. Redox reactions, reactions which involve change in oxidation number of the interacting species. 8.3.1 Types of redox reactions. Number 1, combination reactions. A combination reaction may be denoted in the manner A plus B gives out C. Either A and B or both A and B must be in the elemental form of such a reaction to be a redox reaction. All combustion reactions which make use of elemental dioxygen as well as the reactions involving elements other than dioxygen are redox reaction. Some important example of this category are C plus O2 CO2, 3Mg plus N2 gives out Mg3N2, CH4 plus 2O2 gives out CO2. Number 2, decomposition reactions. In the previous reaction, the reaction was CH4 plus 2O2 gives out CO2 plus 2H2 also is there. Number 2, decomposition reactions. Decomposition reactions are the opposite of combination reactions. Precisely, a decomposition reaction leads to the breakdown of a compound into two or more components, at least one of which must be in the elemental state. Examples of this class of reactions are 2H2O gives out 2H2 plus O2, and all these reactions are happening on heating. 2NaH gives out 2Na plus H2. 2KClO3 gives out 2KCl plus 3O2. It may carefully be noted that there is no change in the oxidation number of hydrogen in methane under combination reactions and that of potassium in potassium chlorate in reaction. This may also be noted here that all decomposition reactions are not redox reaction. For example, decomposition of calcium carbonate is not a redox reaction. CaCO3 on heating gives out CaO plus CO2. Number 3, displacement reactions. In a displacement reaction, an iron or an atom in a compound is replaced by an ion of another element. It may be denoted as X plus YZ gives out XZ plus Y. Displacement reactions fit into two categories, metal displacement and non-metal displacement. A. Metal displacement. A metal in a compound can be displaced by another metal in the uncombined state. We have already discussed about this class of the reactions under section 8.2.1. Metal displacement reactions find many applications in metallurgical processes in which pure metals are obtained from their compounds in ores. A few examples are CuSO4 plus Zn gives out Cu plus ZnSO4, V2O5 plus 5Ca gives out 2V plus 5CaO, TiCl4 plus 2Mg gives out Ti plus 2MgCl2, Cr2O3 plus 2Al gives out Al2O3 plus 2Cr. In each case, the reducing metal is a better reducing agent than one that is being reduced, which evidently shows more capability to lose electrons as compared to the one that is reduced. B. Non-metal displacement. The non-metal displacement redox reaction include hydrogen displacement and a rarely occurring reaction involving oxygen displacement. All alkali metals and some alkaline earth metals, calcium, strontium and barium, which are very good reductants, will displace hydrogen from cold water. 2Na plus 2H2O gives out 2NaOH plus H2. Ca plus 2H2O gives out COH whole twice plus H2. Less active metals such as magnesium and iron interact or react with steam to produce dihydrogen gas. Mg plus 2H2O gives out MgOH whole twice plus H2. 2Fe plus 3H2O gives out Fe2O3 plus 3H2. Many metals, including those which do not react with cold water, are capable of displacing hydrogen from acids. Dihydrogen from acids may even be produced by such metals which do not react with steam. Cadmium and tin are the examples of such metals. A few examples for the displacement of hydrogen from acids are Zn plus 2HCl, ZnCl2 plus H2, Mg plus 2HCl, MgCl2 plus H2, Fe plus 2HCl gives out FeCl2 plus H2. And here reaction 8.37 to 8.39 are used to prepare dihydrogen gas in the laboratory. Here the reactivity of metal is reflected in the rate of hydrogen gas evolution, which is the slowest for the least active metal Fe and the fastest for the most reactive metal Mg. Very less active metals which may occur in the native state such as silver and gold do not react even when the with hydrochloric acid. In section 8.2.1, we have already discussed that the metals zinc, copper, and silver, through tendency to lose electron, show their reducing activity in the order Zn is greater than Cu is greater than Ag. Like metals, activity series also exist for the halogens. The power of these elements as oxidizing agent decreases as we move down from fluorine to iodine in group 17 of the periodic table. This implies that fluorine is so reactive that it can replace chloride, bromide, and iodide ions in solution. In fact, fluorine is so reactive that it attacks water and displaces the oxygen of water. 2H2 plus 2F2 gives out 4HF plus O2. It is for this reason that the displacement reaction of fluorine, bromine, and iodine using fluorine are not generally carried out in aqueous solution. On the other hand, chlorine can displace bromide and iodide ions in an aqueous solution as shown below. Cl2 plus 2 KBr gives out 2 KCl plus Br2. Cl2 plus 2 Ki gives out 2 KCl plus I2. As Br2 and I2 are colored and dissolved in CCl4 can easily be identified from the color of the solution. The above reactions can be written in ionic form as here you can see the ionic form of the reaction. Reactions 8.41 and 8.42 form the basis of identifying Br negative and I negative in the laboratory through the test popularly known as layer test. It may not be out of place to mention here the bromine likewise can displace iodide ion in solution. Br2 plus 2I negative gives out 2Br negative plus I2. The halogen displacement reaction have a direct industrial application. The recovery of halogens from their halides requires an oxidation process which is represented by 2x negative plus x gives out x2 plus 2 electron. Here x denotes a halogen element, whereas chemical means are available to oxidize chloride negative, bromine negative and iodine negative, as fluorine is the strongest oxidizing agent. There is no way to convert fluorine negative ions to F2 by chemical means. The only way to achieve F2 from F negative is to oxidize electrolytically, the details of which you will study at a later stage. Fourth, disproportionation reactions. Disproportionation reactions are a special type of redox reactions. In a disproportionation reaction, an element is in one oxidation state is simultaneously oxidized and reduced. One of the reacting substances in a disproportionation reaction always contains an element that can exist in at least 3 oxidation states. The element in the form of reacting substances is in the intermediate oxidation state, and both higher and lower oxidation states of that element are formed in the reaction. The decomposition of hydrogen peroxide is a familiar example of the reaction where oxygen experiences disproportionation. 2H2O2 gives out 2H2O plus O2. Here the oxygen is oxygen of peroxide which is present in -1 state is converted to 0 oxidation state in O2 and decreases to -2 oxidation state in H2O. Phosphorus, sulfur and chlorine undergo disproportionation in the alkaline medium as shown below. P4 plus 3OH negative plus 3H2O gives out PH3 plus 3H2PO2 negative. S8 plus 12OH negative gives out 4H2 negative plus 2H2O3 2 negative plus 6H2O. Cl2 plus 2OH negative gives out ClO negative plus Cl negative plus H2O. The reaction describes the formation of household bleaching agents. The hypochlorite ion ClO negative formed in the reaction oxidizes the color-bearing stains of the substances to colorless compounds. It is of interest to mention here that whereas bromine and iodine follow the same trend as exhibited by the chlorine in reaction, fluorine shows deviation from this behavior when it reacts with alkali. The reaction that takes place in the case of fluorine is as follows. 2F2 plus 2OH negative gives out 2F negative plus OF2 plus H2O. It is to be noted that with care that fluorine in reaction will undoubtedly attack water to produce some oxygen also. This departure shown by fluorine is not surprising for us as we know the limitation of fluorine that, being the most electronegative element, it cannot exhibit any positive oxidation state. This means that among halogens, fluorine does not show a disproportionation tendency. The paradox of fractional oxidation number. Sometimes we come across with certain compounds in which the oxidation number of a particular element in the compound is in fraction. Examples are C3O2 that is 4 by 3, Br3O8 that is 16 by 3 and in Na2S4O6 the sulfur's oxidation is 2.5. We know that the idea of fractional oxidation number is unconvincing to us because electrons are never shared or transferred in fraction. Actually, this fractional oxidation state is the average oxidation state of the element under examination, and the structural parameters reveal that the element for whom fractional oxidation state is realized is present in different oxidation states. The structure of the species C3O2, Br3O8, and S4O6 negative reveal the following bonding situation. See these, the structure of all three. The element marked with asterisks in each species is exhibiting the different oxidation state, oxidation number from rest of the atoms of the sum element in each of the species. This reveals that in C3O2, two carbon atoms are present in +2 oxidation state each, whereas the third one is present in 0 oxidation state and the average is 4/3. However, the realistic picture is +2 for two terminal carbons and 0 for the middle carbon. Likewise, in Br3O8, each of the two terminal bromine atoms are present in +6 oxidation state and the middle bromine is present in +4 oxidation state. Once again, the average that is different from reality is 16/3. In the same fashion, in the species S4O6 negative, each of the two extreme sulfurs exhibit oxidation states of +5 and the two middle sulfurs is 0. The average of 4 oxidation numbers of sulfurs of the S4O6 negative is 2.5, whereas the reality being +5, 0, 0 and +5 oxidation number respectively for each sulfur. We may thus in general conclude that the idea of fractional oxidation state should be taken with care and the reality is revealed by the structures only. Further, whenever we come across the fractional oxidation state of any particular element in any species, we must understand that this is the average oxidation number only, in reality revealed by the structures only. The element in particular species is present in more than one whole number oxidation state. Fe3O4, Mn3O4, Pb3O4 are some of the other examples of the compounds which are mixed oxides, where we come across with fractional oxidation states of the metal atom. However, the oxidation states may be in fraction, as in O2 positive and O2 negative, where it is +1/2 and -1/2 respectively. 8.3.2 Balancing of redox reactions. Two methods are used to balance chemical equation for redox processes. One of these methods is based on the change in the oxidation number of reducing agent and the oxidizing agent, and the other method is based on splitting the redox reaction into two half reactions, one involving oxidation and the other involving reduction. Both these methods are in use and the choice of their use rests with the individual using them. A. Oxidation number method. In writing equation for oxidation reduction reactions, just as for the reactions, the compositions and formulas must be known for the substances that react and for the products that are formed. The oxidation number method is now best illustrated in the following steps. Step 1. Write the correct formula for each reactant and product. Step 2. Identify atoms which undergo change in oxidation number in the reaction by assigning the oxidation number to all elements in the reaction. Step 3. Calculate the increase or decrease in the oxidation number per atom and for the entire molecule or ion in which it occurs. If these are not equal, then multiply by suitable number so that these become equal. If you realize that two substances are reduced and nothing is oxidized or vice versa, something is wrong. Either the formulas of reactants or products are wrong or the oxidation numbers have not been assigned properly. Step 4. Ascertain the involvement of ions if the reaction is taking place in water. Add H ion or OH ions to the expression on the appropriate side so that the total ionic charges of reactants and products are equal. If the reaction is carried out in acidic solution, use H ions in the equation. If in basic solution, use OH ions. Step 5. Make the numbers of hydrogen atoms in the expression on the two sides equal by adding water molecules to the reactants or products. Now also check the number of oxygen atoms. If there are the same number of oxygen atoms in the reactants and products, the equation then represents the balanced redox reaction. Let us now explain the steps involved in the method with the help of a few problems given below. You can see all the problems. B. Half reaction method. In this method, the two half equations are balanced separately and then added together to give balanced equation. Suppose we are to balance the equation showing the oxidation of Fe2 positive ions to Fe3 positive ions by dichromate ion Cr2O7 whole to negative in acidic medium, wherein Cr2O7 to negative ions are reduced to Cr3 positive ions. The following steps are involved in this task. Step 1. produce unbalanced equation for the reaction in ionic form. Fe2 positive plus Cr2O7 2 negative gives out Fe3 positive plus Cr3 positive. Step 2. Separate the equation into half reaction, oxidation half reaction you can see, and the reduction half reaction. Step 3. Balance the atoms other than oxygen and hydrogen in each half reaction individually. Here the oxidation half reaction is already balanced with respect to Fe atoms. For the reduction half reaction, we multiply the Cr3 positive by 2 to balance Cr atoms. Cr2O7 2 negative gives out 2 Cr3 positive. Step 4. For reactions occurring in acidic medium, add H2O to balance oxygen atoms and hydrogen positive to balance hydrogen atoms. Thus we get Cr2O7 2 negative plus 14 H positive gives out 2 Cr3 positive plus 7 H2O. Step 5. Add electrons to one side of the half reaction to balance the charges. If need be, make the number of electrons equal in the two half reaction by multiplying one or both half reactions by appropriate number. The oxidation half reaction is thus rewritten to balance the charge. Fe2 positive gives out Fe3 positive plus electron. Now in the reduction half reaction, there are net 12 positive charge on the left hand side and only 6 positive charges on the right hand side. Therefore, we add 6 electrons on the left side. Cr2O7 2 negative plus 14 H ion plus 6 electron gives out 2 Cr3 positive plus 7 H2O. To equalize the number of electrons in both the half reactions, we multiply the oxidation half reaction by 6 and write as 6 Fe2 positive gives out 6 Fe3 positive plus 6 electron. Step 6. We add the two half reactions to achieve the overall reaction and cancel the electrons on each side. This gives the net ionic equation as 6 Fe2 positive plus Cr2O7 2 negative plus 14 H positive gives out 6 Fe3 positive plus 2 Cr3 positive plus 7 H2O. Step 7. Verify that the equation contains the same type and the number of atoms and the same charges on both sides of the equation. This last check reveals that the equation is fully balanced with respect to number of atoms and the charges. For the reaction in a basic medium, first balance the atom as is done in acidic medium. Then for each H ion, add an equal number of OH ions to both sides of the equation. Where H ion plus and OH ion appear on the same side of the equation, combine these to give H2O. 8.3.3, that is redox reactions as the basis for titrations. In acid-base system, we come across with a titration method for finding out the strength of one solution against the other using a pH-sensitive indicator. Similarly, in redox system, the titration method can be adopted to determine the strength of a reductant or oxidant using a redox-sensitive indicator. The usage of indicators in redox titration is illustrated below. Number 1. In one situation, the reagent itself is intensely colored. Example, permanganate ion, MnO4 negative. Here, MnO4 negative acts as the self-indicator. The visible endpoint in this case is achieved after the last of the reductant is oxidized, and that is Fe2 positive or C2O4 2 negative. And the first lasting thing of pink color appears at MnO4 negative concentration as low as 10 to the power minus 6 mole dm minus 3, and this ensures a minimal overshoot in color beyond the equivalence point, the point where the reductant and the oxidant are equal in terms of their mole stoichiometry. Number 2. If there is no dramatic auto color change as with MnO4 negative titration, there are indicators which are oxidized immediately after the last bit of the reactant is consumed, producing a dramatic color change. The best example is afforded by Cr2O7 2 negative, which is not a self-indicator but oxidizes the indicator substance diphenylamine just after the equivalence point to produce an intense blue color, thus signaling the end point. Number 3. There is yet another method which is interesting and quite common. Its use is restricted to those reagents which are able to oxidize I negative ions. Say for example, 2CO2 positive plus 4 I negative gives out CO2I2 plus I2. This method relies on the fact that iodine itself gives an intense blue color with starch and has a very specific reaction with thiosulfate ion S2O3 2 negative, which too is a redox reaction. I2 plus 2S2O3 2 negative gives out 2I negative plus S4O6 2 negative. I2, though insoluble in water, remains in solution containing Ki as Ki3. On addition of starch after the liberation of iodine from the reaction of Cu2 positive ions on iodide ions, an intense blue color appears. This color disappears as soon as the iodine is consumed by the thiosulfate ions. Thus, the end point can easily be tracked, and the rest is the stoichiometric calculation only. 8.3.4 Limitation of concept of oxidation number. As you have observed in the above discussion, the concept of redox processes has been evolving with time. This process of evolution is continuing. In fact, in recent past, the oxidation process is visualized as a decrease in electron density and reduction process as an increase in electron density around the atom involved in the reaction. 8.4 Redox reactions and electrode processes. The experiment corresponding to reaction can also be observed if zinc rod is dipped into copper sulfate solution. The redox reaction takes place, and during the reaction, zinc is oxidized to zinc ions and copper ions are reduced to metallic copper due to direct transfer of electrons from zinc to copper ion. During this reaction, heat is also evolved. Now we modify the experiment in such a manner that for the same redox reaction, transfer of electrons takes place indirectly. This necessitates the separation of zinc metal from copper sulfate solution. We take copper sulfate solution in a beaker and put a copper strip or rod in it. We also take zinc sulfate solution in another beaker and put a zinc rod or a strip in it. Now reaction takes place in either of the beakers and at the interface of the metal and its salt solution in each beaker. Both the reduced and oxidized forms of the same species are present. These represent the species in the reduction and oxidation half reaction. A redox couple is defined as having together the oxidized and reduced forms of a substance taking part in an oxidation or reduction half reaction. This is represented by separating the oxidized form from the reduced form by a vertical line or a slash representing an interface. For example, in this experiment, the two redox couples are, you can see that figure 8.3, that is a setup for a Daniell cells. For example, in this experiment, the two redox couples are represented as Zn2 positive Zn and Cu2 positive Cu. In both cases, oxidized form is put before the reduced form. Now we put the beaker containing copper sulfate solution and the beaker containing zinc sulfate solution side by side. We connect solution in two beakers by a salt bridge, a U-tube containing a solution of potassium chloride or ammonium nitrate, usually solidified by boiling with agar-agar and later cooling to a jelly-like substance. This provides an electric contact between the two solutions without allowing them to mix with each other. The zinc and copper rods are connected by a metallic wire with a provision for an ammeter and a switch. The setup as shown in figure 8.3 is known as Daniell cell. When the switch is in the off position, no reaction takes place in either of the beakers and no current flows through the metallic wire. As soon as the switch is in the on position, we make the following observations. Number 1. The transfer of electrons now does not take place directly from Zn to Cu2 positive but through the metallic wire connecting the two rods as is apparent from the arrow which indicates the flow of current. Number 2. The electricity from solution in one beaker to solution in the other beaker flows by the migration of ions through the salt bridge. We know that the flow of current is possible only if there is a potential difference between the copper and zinc rods known as electrodes here. The potential associated with each electrode is known as electrode potential. If the concentration of each species is taking part in the electrode reaction is unity, if any gas appears in the electrode reaction, it is confined to 1 atmospheric pressure. And further, the reaction is carried out at 298 Kelvin. Then the potential of each electrode is said to be the standard electrode potential. By convention, the standard electrode potential of hydrogen electrode is 0.00 volts. The electrode potential value for each electrode process is a measure of the relative tendency of the active species in the process to remain in the oxidized and reduced forms. A negative E means that the redox couple is a stronger reducing agent than the H positive or H2 couple. A positive E means that the redox couple is a weaker reducing agent than the H positive or H2 couple. The standard electrode potential are important and we can get a lot of other useful information from them. The values of standard electrode potentials for some selected electrode processes, reduction reactions, are given in table 8.1. You will learn more about electrode reactions and cells in class 12th. Here is the table 8.1. The standard electrode potentials at 298 Kelvin. Ions are present as aqueous species and H2O as liquid, gases and solids are shown by G and S respectively. You can see this table. Summary. Redox reactions form an important class of reactions in which oxidation and reduction occur simultaneously. Three-tier conceptualization via classical electronic oxidation number, which is usually available in the text, has been presented in detail. Oxidation, reduction, oxidizing agent, and reducing agent have been viewed according to each conceptualization. Oxidation number are assigned in accordance with a consistent set of rules. Oxidation number and ion electron method both are useful means in writing equation for the redox reactions. Redox reactions are classified into four categories: combination, decomposition, displacement, and disproportionation reactions. The concept of redox couple and electrode process is introduced here. The redox reactions find wide application in the study of electrode processes and cells. Chapter done. So if you feel like that this audiobook is helping you, please press the like button. And if you are new on my channel, then you have to subscribe my channel and keep the bell notification on so that you will get the notification for each and every video, because here all videos are very, very important to boost your preparation, because I am preparing all these things जो आपको कम टाइम में ज़्यादा से ज़्यादा रिवीजन, ज़्यादा से ज़्यादा तैयारी करा सकें. अपने दोस्तों के साथ में भी ज़रूर शेयर करिएगा. मिलते हैं नेक्स्ट वीडियो में. तब तक के लिए स्टे ट्यून विद मी. बाय बाय. टेक केयर एवरी